Okay. So this talk is about pseudodeterministic algorithms and the circuit acceptance probability estimation. And this is a joint work with Peter Dixon, Jason Vanderwood, and Vinod Chandra. So, what's a pseudodeterministic algorithm? So, there are probabilistic algorithms that look deterministic. So, this notion has been introduced nearly a decade ago by Gatt and Goldwasser. And my hope in this talk is to convince you that these objects are really fascinating and they are intricately connected to quite a few other seemingly unrelated questions in complexity. Okay, so let's see how much I can succeed. So just to motivate, so let's look at this problem of generating primes. So you are given input 1 to the n, and the goal is to generate an n-bit prime number. So we all know there is an obvious algorithm for this. So you just randomly pick an n-bit integer and check if it's a prime. If so, you output it. So even though it is efficient, so there is a, if I may say so, there is a slight drawback to this algorithm. If I run this algorithm 2 times, I will get very likely that I get 2 different outputs, because each time I may get a different random integer, and that's what I may output as my prime number. So this is the property above of many probabilistic algorithms that are trying to compute a function, especially when the function is a multi-valued function. So these probabilistic algorithms may output different values on different runs. Okay. So the question is, can you design an algorithm, like for example, take the primality, so that if I run it multiple times, each time I get the same prime with high probability. So that's the motivating question. So in addition to being interesting on its own, it has some applications. For example, if you have a distributed environment where all the parties would like to decide on a prime number. So instead of communicating with each other, if you have such an algorithm, all of them can run this algorithm, and they are guaranteed to output the same prime, and that's what they could use. Okay. So motivated by this, so the Gatt and Goldwasser formally defined this notion of pseudo-deterministic algorithm. So if you say a probabilistic algorithm is pseudo-deterministic, if on every input x there is this canonical y, there is a single y that depends on x, such that the algorithm on input x outputs y with probability at least 2/3. And again, as usual, there is nothing particular about 2/3. We can amplify this probability arbitrarily close to 1. So just pictorially, here is an example. On the left side, my algorithm is not pseudo-deterministic, so it's going to, depending on the random choice, it's going to output these 3 different outputs, 3 different correct outputs, A, B, and D. And on the right one, so for all the random choices, or for most of the random choices, I am getting this canonical output A. So my algorithm on the right side, so this is behaving pseudo-deterministically. So is that notion clear?
Is there, like this probabilistic algorithm A, is there a bound on the time or something?
Okay, unless I say okay. Otherwise, we assume all algorithms run in polynomial time. Okay. Thank you. Okay, so since then there have been quite a bit of work in designing pseudo-deterministic algorithm. So the Gatt and Goldwasser, in the same work that defined this notion, they gave pseudo-deterministic algorithms for few algebraic problems. Okay. So for example, finding non-roots of multivariate polynomials and generator for certain cyclic groups and so on. And people looked at pseudo-deterministic NC algorithms for matching. So you know NC algorithms that work pseudo-deterministically that will output a matching, they output canonical matching. And coming to the prime generation problem that we just talked earlier, so there is a very interesting result by Oliveira and Santanum. They kind of come close to it. So they said there is a sub-exponential time pseudo-deterministic algorithm. So the runtime is sub-exponential, but it is pseudo-deterministic, and that is going to generate prime, except that it does not work at all input lengths. It is going to work at infinitely many input lengths. So that's kind of the best known result currently in terms of designing pseudo-deterministic algorithms for primes. Just to say, I think the notion of pseudo-determinism has been studied in various other contexts like sublinear algorithms, streaming, interactive proofs, and space-bounded computations also. Okay, so that's about pseudo-determinism. Let's look at this acceptance probability problem. So this is the classic problem. So given a Boolean circuit, so the goal is to estimate the acceptance probability of this circuit. So if I randomly give an input, what's the probability that the circuit accepts? So, that is the acceptance probability estimation problem. So, we know there is a simple randomized algorithm for this. You randomly choose around 1 over epsilon square inputs and see on what fraction of the inputs the circuit evaluates to 1 and you output it, and can be easily seen that the output is close to the actual value. Okay. But so, this algorithm is not pseudo-deterministic. So, if I run it 2 times, it will go to output 2 different but good approximations. Okay. It's clearly it is not pseudo-deterministic. Now, the question is, can I make this algorithm pseudo-deterministic? So, the main question we are going to look here in this talk is, does this acceptance probability estimation problem admit pseudo-deterministic algorithms? Yeah.
Maybe a naive question.
Mm-hmm.
What happens if you run it a bunch of times and take the median?
Well, again, the median also can shift. So, it is not guaranteed that you are going to get exactly the same median every time.
I want exactly the same number.
Yeah, I want exactly the same number.
And I mean, that's maybe a second question. Do you want the number to be the true number, or you settle down for approximation, right?
All I want is an approximation, a good approximation, but
The same approximation.
The same approximation. So, again, let us see what is known about this one. In the result of Oliveira, Santanam and Holder, they showed that again it can be done to a certain extent. So, the sub-exponential time pseudo-deterministic algorithm, and again this works at infinitely many lengths. Again, it is an average case algorithm. So, you fix a length on many circuits at that length. So, there is a sub-exponential time algorithm that gives the same acceptance or same approximation to the acceptance probability, but it works at infinitely many lengths. So, that is a positive result. So, it kind of gives a hope that maybe there is such an algorithm for this APE. Maybe we can get a polynomial time pseudo-deterministic algorithm. And more recently, there is a very interesting result that says that, well, indeed, if I can find such a pseudo-deterministic algorithm for APEP that runs in polynomial time, then BP time admits a hierarchy theorem. So, it is a long-standing open question in complexity theory whether BP time has a hierarchy theorem. So, this result shows that designing a pseudo-deterministic algorithm for APEP solves this open question. Okay. So, the kind of say the first result kind of gives a hope that maybe it is possible. Second result maybe indicates that maybe it is not that easy, or maybe this is a way to do a hierarchy theorem. Okay. So, the goal of this talk is going to show results of this kind about what can happen when if you can design pseudo-deterministic algorithms for APEP. Okay. We're going, yep.
Just I want to ask a question. So we know hierarchy for BT time with 1 bit of
with 1 bit of advice we know. Yeah.
So
we want an absolute hierarchy theorem.
I see.
Okay, the first result is we are going to show a completeness result. We are saying that if I can get a pseudo-deterministic algorithm for APEP, so that is going to imply pseudo-deterministic algorithm for a broad class of problems. Okay, so what are these kind of problems is, let me just define the class when I say broad class. The SearchBPP. So just to define this SearchBPP, we have a relation over sigma star plus sigma star, and the search problem is given y, you want to find a witness for, sorry, given x, you want to find a witness for x. So find a y such that x, y is in R. So we say the search problem is in SearchBPP. If R is in BPP, I can decide the relation BPP, and there is a probabilistic polynomial time algorithm on input x, outputs y, such that x, y holds. Again, just because a problem is in SearchBPP does not necessarily imply the algorithm that is going to output a witness, it may not be pseudo-deterministic. So, again, if an input x has multiple witnesses, so different runs of this algorithm might output different witnesses. Okay. So, the question is that can we design pseudo-deterministic algorithms for SearchBPP? Okay. So, the completeness result we say that, well, this APEP is complete in the following sense. So, if I can design a pseudo-deterministic algorithm for APEP, then every problem in SearchBPP, I can get a pseudo-deterministic algorithm. Again, if you think of the prime generation problem, I can formulate it as a SearchBPP problem. So, in fact, I can have a pseudo-deterministic algorithm for generating primes. That is what we can get. And also, we can say that take any function that admits epsilon delta approximations, and all such functions also can be made pseudo-deterministic. So, for every efficient approximation algorithms, I can make them output a single approximation, correct approximation. So, that is the completeness result in this question. Okay. So, is that clear? So that is the first result about this APEP. So, I am going to skip the proof of this one. It is
Sorry, maybe I take you back.
Yep.
Maybe a clarification. So when you say this epsilon delta, it's like in the back learning sense?
No, it's like FPRAS.
The probability epsilon, you get something which is delta close or something like that?
Yeah, with probability, yeah, it's based, or in this terminology with probability 1 minus delta, you get epsilon close. Yeah. It's kind of like a FPRAS kind of analysis. Yeah. Again, you can show that based on this, there are a few other complete problems in this sense. So, like estimating the entropy of a Boolean circuit or estimating the collision probability, they also turn out to be complete in this context of pseudodeterminism. So, the next part we are going to talk about a few complexity theory consequences. So, we already seen one consequence that says that a pseudodeterministic algorithm for APEP is going to give a hierarchy theorem, so which is a long sought result. Okay. So, the main informal results we are going to say is that in addition to it is going to solve a few other open questions in complexity theory, and it also very interesting, it explains the gap between the promise classes and their language counterparts. So, in earlier talks we have seen some discussion about PromiseBPP versus BPP and why is that certain result require this promise class as opposed to a standard. So, in general we are interested in derandomizing BPP or what consequences we have if you derandomize BPP, but it so happens that sometimes PromiseBPP plays a role in establishing such results. So, this will explain the gap between the promise problems and the language counterparts. So, what does that mean? So, let me define this notion of promise problems. They are introduced long back by Evans, Selman and Jacobi. So, a promise problem is nothing but a pair of disjoint sets. So, pi y and pi n. So, pi y is the set of all s instances and pi n is the set of all no instances. We say an algorithm solves a promise problem means it is going to accept every input from pi y and rejects every input from pi n. And if the input is, the promise does not hold, which means the input is neither in pi y nor in pi n, the algorithm may behave whatever way. On some inputs it may accept, some inputs it may reject. And we say a solution to a promise problem is a set that will distinguish these s instances from no instances. It is a superset of the s instances and it is disjoint from the no instances. Okay. So, now let us define this PromiseBPP formally. So, a promise problem is in PromiseBPP. If I have a probabilistic polynomial time algorithm that solves this. So, which means, so if you are an S instance, you are going to accept with probability at least 2/3. On a no instance, you are going to accept or reject with probability at least 2/3. But when the promise is not satisfied, this machine M may not have a BPP type behavior. So, on such inputs, maybe the acceptance probability could be close to half. So, that is what a PromiseBPP means. So, the question we can ask is that is PromiseBPP equals to BPP? So, which means if I take a PromiseBPP problem, does it have a solution BPP? Or put it other, can I take this machine M and can I make sure that its behavior on instances where the promise does not hold, there also can I make sure that its behavior is a BPP type behavior. So, that is what this question of PromiseBPP is same as BPP mean. Okay. So, interestingly we can, okay, for that why we care about this PromiseBPP. So, if you look at these questions, like suppose if I can derandomize BPP to P, does that imply derandomization of MA to NP? Or if I can derandomize RP to P, does that imply derandomization of BPP? Or does BPP have complete problems? If you look at all these questions, we do not know the answers, okay, to any of these questions. But if I look at the promise analogs of these things, we know affirmative answers. Like if PromiseBPP is in P, then I can derandomize MA to NP, and similarly promise RP in P means BPP equal to P. So, this kind of says that it is intriguing to understand the relation between these promise classes and the language counterparts. Okay. So, what is the gap? So, the first result is I can relate this to pseudodeterminism. Okay. So, this is exactly the same. Designing pseudodeterministic algorithms for APEP is exactly equivalent to understanding the difference between PromiseBPP and BPP. So, if APEP admits pseudodeterministic algorithms, if and only if PromiseBPP equal to BPP. So, that is the result. So, it kind of explains the difference between these promise classes and BPP. So let me give you one direction of the proof, which is easier direction. So let's start with a pseudo-deterministic algorithm for APEP. And if I take a promise problem in PromiseBPP and say M is a probabilistic machine, so look at this algorithm. So on input X, you just convert the computation of Mx into a circuit Cx and run my algorithm A, which is a pseudo-deterministic algorithm that is supposed to approximate the acceptance probability. If it's bigger than half, accept, otherwise reject. So that's it. It's pretty straightforward and simple algorithm. Okay. So now we can claim that B has a BPP-type machine. So again, if the input is from S instance, M itself is a accept probability 2/3, so C accept with probability 2/3. So my A is going to output a value that's bigger than half with very high probability. Okay. So you're going to, my B is going to accept this input, and similarly B is going to reject every no input. Again, the troublesome case is when the input does not satisfy the promise. So let's take an input that's neither in an S instance nor a no instance. So my machine is going to accept that with some probability P. So which means the acceptance probability of the circuit Cx is P. But when I run my pseudo-deterministic algorithm A on Cx, what happens? It's going to output this canonical value V that's close to P, which means most parts of this machine are going to output a value V. So all the parts are going to output, or most of them are going to output a single value V. So that could be either bigger than half or less than half, it doesn't matter. If it's bigger than half, you're going to accept, that means most paths will lead to acceptance. If it's less than half, then most paths are going to reject. So that shows that B is a BPP type machine. So that's one direction. And the other direction is a little bit more involved, so I'll just skip the proof of that. Any questions so far? Okay, so you get a nice consequence or a different proof of the Liu, Olivares and Theorem's proof. So long back, Barak showed that if PromiseBPP is in BPP, then I have a BP time hierarchy theorem. So this gives an alternate proof of this one, that if APEP has a pseudo-deterministic algorithm, then PromiseBPP is same as BPP. So I have a hierarchy theorem. Okay. And we're going to get, I can relate this question to circuit lower bounds also. So one of the interesting questions in circuit complexity is that what's the smallest complexity class that does not have linear size circuits? Ideally, we would like to say P does not have linear size circuits, but we are far away from doing that. So, but there has been some series of works that shows that, okay, Kannan showed that sigma 2 does not have linear size circuits. That has been improved to ZPP to the NP, and the best known or the smallest complexity class that we know currently is S2P. So the next smaller class is MA, and below that is NP. So can we show that MA or NP do not have linear size circuits? So again, this has been a very pretty long-standing open question.
Who has a result that gives
It's close to it. Okay, I won't talk about that yet.
Okay.
So what we can show is that if APEP has pseudo-deterministic algorithms, then MA does not have linear size circuits. Okay. The proof is just follows by earlier result combining with Rahul's result. So Rahul showed that promise MA does not have linear size circuits. Again, it's easy to see that promise MA is nothing but there exists PromiseBPP. Now if APEP has pseudo-deterministic algorithms, PromiseBPP is nothing but BPP. So my promise MA, I can say it's there exists dot BPP, so which is in MA. So I get MA does not have linear size circuits. Yeah.
So you actually get a bound against this potentially subclass.
Yeah, a smaller class.
NP to BPP, right?
Yeah, NP dot BPP, that's what I actually get. A slightly smaller class. So that's one consequence. Again, that relates the circuit lower bound question to designing the pseudo-deterministic algorithms. And again, we can show a few other results relating to MA, saying that if APEP has pseudo-deterministic algorithms, then MA has complete problems, and you can get hierarchy theorem for MA time also. So that's about the consequences in complexity theory. So the next few minutes, I'm going to talk a little bit about the impossibility results, what makes it difficult to design the pseudo-deterministic algorithms. So for this, let's talk about this notion called multi-pseudodeterminism. Again, if I look at my algorithm that estimates the acceptance probability, it's easy to modify this algorithm saying that instead of it's going to output at most 2 values. all you do is that you take this interval 0, 1, you divide into subintervals which are size epsilon. Whenever you see an output, round it to the closest or to the right end or left end of it. So you may lose a little bit in the approximation guarantee, but it's easy to see that. So I'm going to get two distinct outputs. So this motivated Goldreich to define this notion of k-pseudodeterminism. So again, a probabilistic algorithm is k-pseudodeterministic for every input x. So there is this set Sx of sign at most k, and with very high probability. In this case, the probability is to be at least k plus 1 or k plus 2. An algorithm is going to output a value in this set Sx. So that's this notion of k-pseudodeterminism. So go to look at this 2 APEP problem. So which is, I'm given two Boolean circuits, C1 and C2. My goal is to estimate acceptance probability of both of these circuits. So what kind of pseudodeterministic algorithms I can get? Obviously, I can get a 4 pseudodeterministic algorithms. I run the 2 pseudodeterministic algorithm for C1, and next I run the 2 pseudodeterministic algorithm for C2. I got 4 choices. Okay. So that's straightforward. Very remarkably, Goldreich showed that I can slightly improve this. I can make it 3 pseudodeterministic. Instead of 4 choices, I can cut down to 3. So there is 3 pseudodeterministic algorithm for this problem. So what we're going to ask is that, can I improve it further? Getting pseudodeterministic might be difficult, but can I get a 2 pseudodeterministic algorithm for APEP? So next result shows that it's not possible in the uniform query model. What does it mean? So the known algorithms, or the Goldreich's algorithm, or the known algorithm to estimate the acceptance probability, all they do is that they randomly take a string and then evaluate the circuit on it. So if you are restricted to such type of algorithms, so you cannot hope to get a 2 pseudodeterministic algorithm for this one. How much time I have?
Couple.
So let me just give a quick overview about the proof of this one. So let's start with the 2 pseudodeterministic algorithm A. Assume that we have a 2 pseudodeterministic algorithm for this problem. So take this 2 to the n dimensional square and consider the standard grid partition about it. So then, for each integer between 0 and 2 to the n, I am going to associate a circuit, a CU. It evaluates to 1 on the first U strings, and on every other string it evaluates to 0. So I am going to argue the behavior of this A on only circuits of this form. It is a very restricted class of circuits. So for each lattice point UV in this square, so associate this circuit CU and CU. And let's see how this algorithm is going to behave on such circuits. The first tool is this distance lemma. So if I take 2 lattice points P and Q that are close to each other, or the adjacent lattice points, which means their coordinates differ by at most 1. Then if I look at the distribution of my A, output distribution of A on this U, on this U1 V1 and U2 V2, then they are pretty close. So the distance between these two distributions is very small. So that's the distance lemma that can be proved. So that's 1, 2. So the next one is we're going to look at a 3 coloring of the unit square. So there's nothing magical, we just take 1 half to be blue and the remaining half divided into 2 parts, giving 2 different colors. Okay, so we have that coloring in mind. Then I'm going to use this and as my pseudodeterministic algorithm to color the lattice points of my square. My square are divided into this n by n grid partition. So look at a lattice point UV. Now if I run the algorithm A on the circuit associated with this lattice point CU and CV, I am going to get an output AB. Okay. Look at what's the most likely output. Okay. So this output AB is that both A and B are values between 0 and 1. So they will lie somewhere in this unit square. So maybe they are in the blue region or in the yellow region or the pink region. Whatever region it lies, that's the color of my lattice point UV. So that's the coloring I'm going to define. So just a few observations. So since A is a 2 pseudodeterministic algorithm, so its output belongs to a set of size 2 with probability at least 3, 4. So which means the most likely output probability is at least 3. So that's an observation. So now I'm going to, so again this is pictorial representing, if I look at this point Q, so I'm coloring all these grid points. If I run my algorithm A on this Q, it's running in the blue region, so it's colored blue. 'blue'. 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 lattice point gets a color. So I'm going to apply Sperner's lemma. So it shows that there is a unit square of the partition. If you look at the corners of that unit square, so that square will have all 3 distinct colors. So here, so each of these unit squares, all the 4 corners get a color. So it's going to say, well, there should be a unit square. So where I see all 3 colors. So that's what you can guarantee from Sperner's lemma. So once we have that, so let's focus on those 3 points where I get 3 distinct colors. So let's call them P, Q, and R. So if I run my algorithm A on the circuits associated with P, I get an output A1, B1. And if I run my algorithm A on the circuit associated with this point Q, I get this A2, B2. And similarly, I get this A3, B. Now, the thing to notice is that these values A1, B1, A2, B2, A3, B3, they're all distinct because they all have different colors. They went to the different regions of my unit square. So they're all distinct. Okay. And again, the most likely output is probability is at least 3. So once we have this, now the rest is combining this with distance lemma, and we get a contradiction. So let's look at this algorithm A on input this C, the circuits U1, B1, and it's going to output this value A1, B1 with probability 3.8. Yeah. And if I look at these adjacent points, so since Q and R are adjacent to P, when I run it on U1, B1, when I run it on Q, it's going to output A2, B2 with high probability. But since P and Q are adjacent, when I run my algorithm A on U1, V1, it's going to output A2, B2 also with probability close to 3.8, and it must output A3, B3 also with probability close to 3.8. So, but if I sum up all those probabilities, I get more than 1. So that's a contradiction. So that contradicts that my A is too pseudodeterministic. And finally, I can generalize this. We can generalize this result and express in terms of the query complexity. It basically says that there is an exponential separation between the k plus 1 pseudodeterministic query complexity and k pseudodeterministic query complexity in the uniform and non-adaptive query models. Okay, so that ends, and then the few open questions are like are the other complete problems. And if I have pseudodeterministic algorithm for APEP, can I get MA equal to NP, or NP does not have linearized circuits? Or more interestingly, can I get a pseudodeterministic algorithm for APEP or the prime generation problem? Okay. Just one slide. Just want to dedicate this on a personal to my advisor Alan Selman. Having worked on all the topics related to this talk, promise problems and pseudodeterminism in the context of non-deterministic computations. Thank you.